The broadcast is now starting. All attendees are in listen-only mode.
Okay, welcome everybody. I still see some attendees popping up in here. It's 2:30 Atlantic time, 1:30 Eastern time. I'll give it another couple seconds here. Let's see the attendees numbers slow down before we begin. Maybe another 30 seconds or so. Click to Okay, welcome everybody. WaterHammer in steam systems, causes, fixes, maybe some prevention tips. Hopefully you get something from the presentation. My name is Jeffrey Scott Burrell, sales engineer, Atlantic Canada. About 25 years in the steam delivery, steam return, condensate return business. But the presentation is not about me, it's about you. I'll start with a couple of apologies. Normally do this presentation over a lunch and learn, and unfortunately, due to the current conditions, can't bring you lunch, which is normally the best part of the presentation. Apology number 2 is I'm not live at your facility, and this presentation is not a two-way street, as we can say, so I can't engage you in questions during the conversation, which is kind of disappointing for me. You guys are my guinea pigs for my first ever presentation on a webinar. Objective today. The objective today is just to create peace of mind so that you can tackle your WaterHammer issues. We have a lot of people signed up today and a very wide group of people. So a lot of great questions, and hopefully we answer most of them. This webinar was not designed to be an in-depth forensic view of WaterHammer. It's just a general overview of WaterHammer in our systems, and we hope you get something from it. If we don't answer your questions, of course, we're only a Zoom call away. Okay, let's talk about what we're going to talk about, if we get it to work right, and then don't go too fast. Understanding WaterHammer in steam systems. Okay, let's define WaterHammer first off. Then we'll discuss addressing WaterHammer as we design our systems, or maybe, there's a lot of people online that have plans here. So as we troubleshoot our WaterHammer in our systems, we'll talk about some of those issues, and then we'll go through some real world examples that, being in Atlantic Canada, I always brag about Atlantic Canadians being the smartest, people on earth, basically. And in the last 6 months, I've been on site for a number of steam applications, and I still see today some WaterHammer problems out there. I'm going to go too fast. Sorry, guys. Bear with me. It's my first one. And get rid of the mouse. All right. So WaterHammer. So I was, thinking about doing this presentation, and I did what everybody else does. I Googled it. What is WaterHammer? Basically, it's a hydraulic shock that causes waves, noise, damage in our piping system, and that's just what it is. We're going to talk about WaterHammer only in steam systems, not in water systems so much today. Types of WaterHammer and steam systems. The first one we know as a slug flow or pipe clearing transient. We'll talk a little bit about the definition of that and the impact pressures formed by that. Talk about steam bubble collapse. I call this cavitation. Everyone seems to know cavitation for what happens in pumps. In my mind, the way my mind works, steam bubble collapse is cavitation, or WaterHammer in steam systems. Draining pipes in the presence of steam. This one nobody talks about, and as it turns out, it's the biggest source of our water hammer in our steam and condensate systems. And I'll try to explain why that is in the future slides. Column closure or pump startup causes issues in our plants, knocking and banging, so we'll discuss those. Okay, pipe clearing transient slug flow. So a lot of sales engineers, steam experts would have you think that slug flow is a very detrimental or catastrophic issue in piping systems. So let's do some math here. So basically, our steam systems carry water and condensate, and if you can see this GIF file, what happens is as that condensate builds up in our piping system and the wave touches the top of the pipe, it has to touch the top of the pipe. But as soon as it does, we create a slug flow that grows at the velocity of the steam in the system. We can approximate this impact force at the first elbow or first valve or first stop as impact pressure Pmax equals PV squared, where Pmax equals, rho V squared, where rho is the fluid density of water and V is the slug velocity. I'm going to hammer through these real quick here. So if you do the math and you cross out all your units of measure and you double check and come up with some numbers, the force of impact turns out to be, according to my math, in the range of about 265 PSIG equivalent. Now, coincidentally, this is pretty close to ANSI 150 class piping, but a lot lower than you would suspect that impact pressure to be at a nominal design velocity of my steam system of 100 miles an hour or 150 feet per second. Okay, so keep that in mind. I'll hit enter. And we'll look at the next one, steam bubble collapse, or what I call cavitation. So cavitation occurs when we get a steam trap bubble trapped in a cooler pool of condensate or water, and that bubble collapses. And hopefully you can see that by the simple diagram here, which I borrowed from a nice water hammer report, which we'll reference at the end. We'll go to the next slide. And now we'll try to predict the impact pressure this will have on our steam piping system with this type of water hammer. So now my impact pressure max equals PCV. So we replace one of the V's with the speed of sound in water, which, approximately 4,300 feet per second. So what this does to our steam system, and it does have a considerable impact pressure difference, somewhere in the range of 10 to 100 times greater than slug flow. And that's due to that speed of sound in water. And the big range and difference between the 10 and the 100 is due to our piping system, which, is due to the design and the rigidity of our piping system. And in some respects, it's due to how well we get rid of the non-condensables in our gases. Unfortunately, the better we are at getting rid of the non-condensables, the higher the impact pressure is, because that gas acts as a sort of a dampening effect. So it's the opposite of what we're trying to do. So our goal here at the end of the presentation is try to eliminate water hammer. As I said before we started or going through these types of water hammer, draining pipes in the presence of steam, typically in the horizontal direction, sounds simple. Sounds like anybody can drain water from steam. But if we think of draining in a couple of different terms, if we think of draining as opening an isolation valve and draining steam into our process heat exchanger, it's the same. It has the same effect. The math is the same. or if we're draining a steam line or starting up a steam lining, we're draining to atmosphere, has the same effect. Or if we picture draining as condensate leaving a steam trap, we're draining the condensate from one side of the steam trap and we're draining it into the downstream side of that steam trap. That's still draining, draining pipe or draining our systems in the presence of steam. So this one is kind of interesting because it has a major impact on our water hammer that we see typically in our systems. Oh no. All right, let's start over. Sorry, guys. I like to blame this. Let's see, start there. Okay, I got a sensitive mouse. Okay, so this study on water hammer is it's invasive, it's forensic, it is what it is. But if we look at some of the zones, and this is so what we have on the left-hand column rising is the water flow rate or the draining flow rate of condensate. On the x-axis, we have temperature differential increasing, so basically subcooling of our condensate. So if we have little or no temperature difference, and we're at the bottom of that curve or plot, we're in a stable zone. We don't really have water hammer. So if we have no subcooling or no temperature difference between one side or the other, we really don't get that much water hammer. Now, if we have very, very slow drain rates, it doesn't matter what the subcooling is. We have we remain in that stable zone as we go from left to right as we subcool. So if we drain our systems very, very slowly, we still remain stable. But if we combine the two, if we drain very, very quickly and we have large subcooling, we fall into that water hammer region. And this study basically says to me in a common sense kind of way is we need to drain really, really slow, or we have to have no temperature difference draining one side to the other, and we'll remain stable. Keep that in mind, as I think this is the cause of most water hammers in plants, and why sometimes it happens and sometimes it doesn't. Okay. Go through column closure. Again, pumps turning on and off in a liquid system can cause some water hammer. And basically it's due to either leaking check valves or a column of water that's suddenly turned into flash steam. Oh my goodness, why am I going backwards? Sorry, guys. Previous. Oh my goodness. Apologies. Go over. I have a very sensitive something here, probably a mouse. So yeah, so when our pump clicks on and we have a vapor column, typically in a condensate system per se, we're going to get a slug of water. Depending on the force of the pump and all that stuff, we're going to get some banging in the pipes at the first elbow there when we hit that void. Next one's kind of interesting is what we're showing is a typical large-scale piping system, possibly in a hospital or a university where this is common, where we're discharging steam traps and pump condensate into the same line. So as long as our piping's good and we don't have any pockets where flash steam can form, we shouldn't get any slug flow, but we may get pipe bubble collapse. Might get pipe bubble to collapse. So in this situation where we're pumping and discharging steam traps, we could get some slug flow, water hammer, and worst case, we could get some cavitation or bubble collapse. But just keep that in mind. Interesting one. Okay, so this is the next step. Might get a little off track, as I can say, because I'm trying to explain this without a conversation with you guys, so, and girls. Um, uh, and what goes through my mind when I'm trying to design a system or troubleshoot water hammer systems. So saturated steam and piping systems is always, if we go into the math, it's two-phase flow, but the way I like to view it is two distinct flowing systems. So we have steam, saturated steam, and water, and they may or may not be going in the same direction. In a one pipe steam system, the water actually goes in the other direction. So we got to keep that in mind. We also got to separate our system into hot condensate lines. So when I look at condensate lines, and they're all labeled the same, I try to distinguish between hot condensate and pump condensate. Hot condensate, I picture those as steam lines at 0 psig. And that changes, and it's not 100% accurate, but it helps simplify in my mind when I'm trying to troubleshoot water hammer. And pump condensate is basically a water system. It's a warm water system, and it can be a hot system, but it's basically a water system. So we should distinguish between those three, and probably label them a little differently than we do today. We could break that down even further, but I'm going to run short of time on breaking those down. But we should label those, obviously, or at least in our minds when we have water hammer issues. We should agree not to mix these three lines. If you really want to avoid water hammer, just do not mix those lines. And this is the part where I sort of added in after I seen all the people that signed up. When we're designing our steam systems, we need to design all our steam systems so that we need to view all our valves in the closed position. And we also have to view all our valves as if they're leaking, which sometimes is hard to do. But again, it's part of troubleshooting, part of design in designing a first-class steam system. I'll just through this here quickly. So back to, I just want to introduce a couple basics of our steam supply system. We do not want water in our steam systems. That's the idea. Water is a consequence of saturated steam. So we want to pipe it properly. Don't want to use concentric reducers. We just want the steam to flow and the water to be separate from the steam and not create those waves in slug flow transients. The next picture is of a strainer, and it's a little bit of a pet peeve of mine. But if you carefully and you look at that strainer, a couple things come to mind. In a steam delivery system, and we put our water strainers or our fancy strainers in line, and then we put the yoke down, and then we fill the yoke with water. Creates two problems. Well, creates a number of problems, but the big one is we've got a puddle of water there, or a huge volume of water. And two, we create a pinch point for the steam, which creates a very high velocity region and may impact the performance of our heat exchangers, et cetera, et cetera, et cetera. So if we look at that picture and we roll that strainer on its side, we create a much more effective strainer, and we get rid of that volume of water in that strainer. And then if we get back to, the impact pressures, because most of the time, even though we try to convince people to put that strainer on the side, we get to site and it's up and down. I like to make any strainer on the steam side made out of carbon steel, which at least gets me to the ANSI 150 class. Steam takeoffs, pretty basic. We want to take off from the top of pipe and not the bottom, as we'll send that water, potentially causing water hammer, to our equipment and our valves, our control valves, et cetera, et cetera, et cetera. Drip traps. Again, I'm going to show a picture later on. I didn't think this still happened, but obviously it does. we need to get that water out of our steam delivery system. And at 100 miles an hour, we need to make those pockets of the correct size. I'll leave all the sizing to the next steam design webinar, but basically we need a nice pocket to get rid of that water in our steam delivery system. So one of the things that I talked a little bit about is designing our steam systems with the valves closed and or leaking. So this is the typical top of a boiler. You have a stop check valve and an isolation valve, and there's nothing in between the two. And in boiler case, we could have steam on the backside of this, but we really need to picture getting rid of this water at all times, whether that's a drip trap between these two valves or moving the valves. We just have to think about that and visualize water in our system developing while our valves are closed. Yeah, hopefully that's clear. So as I was preparing for this presentation, I tried to make a list of all the things that I've seen that cause water hammer in our piping systems, and I stopped typing because I keep seeing all these things over and over and over again. From the simple things like no insulation, no drip traps, steam trap issues, steam traps above lines, submerged lines, operating my plant too quickly, a number of things. So there's a lot of things that go into causing water hammer. It's not just one thing. So again, if we go back to the basics and looking at where the water is, how it's going, how we're mixing that water, maybe we can solve some of these problems one at a time. So some real world examples. Again, these are just from sites I've been on in the last 6 months. Excuse me. Drip trap in front of a process heat exchanger. Again, it's just too small. Our equipment is going to take a lot of the water in our piping system that's formed overnight. We have lack of insulation, and it's throw it into our heat exchanger, causing water hammer. These drip traps need to be sized appropriately to get rid of that water so we don't throw it into our equipment. This is very, very common, and it's steam lines or steam traps installed above the line to be drained. Picture here, I got a number of red lines there that show the steam traps off the side of the line. But a steam trap is also a liquid level controller. So steam traps like to maintain level, and they can be used not only in steam systems, but also in refrigeration systems for, liquid level control. So we need to look at our piping systems, we drain appropriately, and drain off the bottom. And these type of drain systems just cause water hammer. Steam traps. There's a reason, steam traps companies are, still around today. There's what I consider 3 or 4 really, really major ones, but steam traps are a necessity. We need to install them correctly. This was at a site here, 10 minutes from my house. I went, he said, I have a water hammer issue. The steam traps were installed upside down. Steam traps can also not work properly. They can fail closed, causing water hammer as we can't drain, causing differential temperature problems, as discussed earlier, and they can fail open. Fail open steam traps waste energy, of course, but they may cause differential pressure issues if they are large enough in our condensate return system, causing backup of condensate in our system. And this was recent. This was at a job site I won't mention. So we got a call, all our steam traps are failing. Their floats are all crushed, destroyed. There must be a malfunction with our traps. They don't work. Go to site, and we have a condensate return line. I can't see it on my screen, but hopefully you guys can see it on your screen. There's a big F&T steam trap on the right-hand side there. Well, that F&T steam trap was piped perfectly, had a nice strainer, nice isolation valves, et cetera, except that it was after all the process equipment steam traps. And basically, if we look at steam traps as liquid level controllers, it was trying to maintain a flooded state in the entire condensate piping system upstream of the steam trap. And the water hammer was obviously quite substantial. Okay, this is very, very common. Seen this at multiple hospital sites recently. Looks great, 100%. Looks like a steam header. Except these are condensate return headers that were piped in perfectly by the contractor, by the engineer. They look great. In these instances, we're bringing back pumped condensate, flash steam from steam traps, high pressure condensate, medium pressure condensate, all to a nice header. And then we're forcing all that condensate back into a receiver tank, which is right next door, because it looks pretty, I guess. And we're mixing those condensate lines, which we're treating as hot condensate lines. If we're treating that at 0 psi steam lines, we're mixing steam, pumped condensate, and different flash. So we're getting pockets of steam that collapses and causes, a real pain in the butt water hammer all the time, and for years and years and years. And like I say, it looks pretty. It's just not right because we're mixing all those different types of condensate. And check my clock here. I got 3 minutes to go through this one. And it's going to take me longer. I apologize. So here we have our typical process heat exchanger, Schelln's heat exchanger, process water glycol on the downstream side of the process side. We've got our strainer pointing straight down. It looks great. Sending all that water into a control valve. We've got nice differential pressure gauges on it to measure the differential pressure. Obviously, we're modulating down. Sending that condensate into the heat exchanger and then to a steam trap. So, looking at this, there could be 1, 2, 3, maybe 4 different types of water hammer in one system, happening all at the same time, causing you grief. So we've got the slug flow from the strainer. We've got modulating pressure going into a steam trap, which is discharged into some type of condensate system. I'm not sure what, but that may be causing a water hammer. And then we look at the process side. It's one of those things where in today's energy efficient world, we're really not looking at the process side so much. So if this heat exchanger is heating a building or heating a plant, and I'm not carefully monitoring the pressure, if I'm trying to save energy at night, and I'm changing the flow and/or the pressure of my process system, potentially under a no flow or low flow situation, I could have a call for steam, and my steam pressure on the steam side is greater than the steam on the process side. Happened recently, and I was called in. So this skid started jumping off its moorings, and they just couldn't figure out why. It's not really water hammer. What it is called is localized boiling. So localized boiling is a huge problem in a no flow, low pressure situation, and it just basically takes out the steam trap. Might take out your heat exchanger, so it could be very expensive. So something to be thinking about, looking at, maintaining a process temperature higher than your steam pressure. Okay, a quick summary of what we're trying to do here today and why we're here. Basically, what we're trying to do is prevent water hammer and troubleshoot water hammer. So how we do that is we're trying to look inside the pipes and see what's going on. How do we do that? visualize your valves closed, like we discussed before. Visualize them leaking. Trying to figure out how or why condensate is building up in our condensate or in our process system, and why is it causing water hammer. The big thing discussed in the initial slides was draining. We're always draining. Everything's draining. We need to drain at close to temperature of our steam temperature. So our condensate temperature has to be the same as our steam temperature, or very, very close, and then we prevent water hammer. Are we mixing different types of condensate? We can mix different types of condensate with engineering controls. We can. But if we're having water hammer, we're not doing it properly. So we have to consider that. Are we mixing high temperature condensate, pump condensate, without engineering controls? Do we have steam pockets forming in our system, in our condensate system? Yeah, maybe, maybe not. But we need to have a look at that. And are our steam traps working? Failed cold steam traps, if they should be working, they gotta be hot. Our first check is make sure all our steam traps are hot. And then if we are getting water hammer, are we having slug flow in our high temperature condensate return system, which is basically a steam system at 0 psi, and we're getting slug flow. All right, sorry guys, I gotta hit the right button. I have a bunch of references that I used. There's a couple more that I have. I have a couple of reports on transient water hammer, et cetera, et cetera. If you guys are interested, send me an email. I can give you what you need. Again, thank you very much. Jeffrey Scott Burrell, Atlantic Canada Sales Engineer. If you need me for anything.
Okay, thanks.
Spyrex.ca.
Thank you, Jeff. We will do some questions as well. I have a few questions I'll read out. We'll just discuss those too. There was a few questions earlier on, and I know most of you would, at least the ones who have seen it. The question was basically, if you have any questions, just in case, if you guys didn't notice it yet, there's a questions tab on there. Please enter your questions in there as well. But one of the questions we had was water hammer in existing radiator systems, and will adding control valves at the rads make water hammer worse or have no effect? The stuff I've seen, the control valves will make the water hammer a little worse because that changes the pressure inside the radiators, the steam radiators that you have. Typically, water hammer that I've seen at different places is because of condensate not draining out, and it is done properly in low steam pressure radiator applications by using a vacuum pump system on the condensate side. So that's basically my take on it. Jeff, you have any thoughts on this?
Mine were identical. The really sorry, I didn't design these systems, and I know our customers are stuck with them. We could have fixed it in the design stage by keeping the condensate downstream of the steam trap at the same temperature as the downstream temperature after the discharge of the steam trap. Simple design fix, could have been done at time of design, but now we're stuck with it. Really, the only solution is a vacuum pump system, and it'll solve all your problems.
Yeah, okay. The other one I have is how to rectify water hammer in existing systems. I mean, Jeff, I know you did talk about separating these condensate, high pressure condensate and low pressure condensate, or high pressure condensate and pump condensate lines. And I'm pretty sure most of our customers as well. How do you address that? Because sometimes you have different pressures and there's only one high pressure line condensate or one high pressure condensate trap, and you can't really run a completely different line for it. One way we've seen is we've actually also supplied what we call inline condensate mixers. Now they don't eliminate water hammer, they reduce water hammer to an extent. So unfortunately, it depends on what it is, how much high pressure condensate you're getting as well. So there's a few things in there that need to be looked into, and it can't be a lot either. And the other way was also to do a flash tank, knock the high pressure condensate down to lower pressure, and then mix them at similar pressures that way too. So Jeff, what do you think about rectifying in already existing systems? If someone already has piping already done, do you have any other ideas?
It just brings to mind a lot of questions that come to mind at site. But if I have a single steam trap, if we back away, do I need to capture that flash steam is my first thought, or can I subcool it? Take it to drain, basically take it to grade. If that's not an option, a very, very tiny letdown station, if I have a low pressure system I can tie into, I don't need any fancy controls. I can just do a simple vessel, knock it down, and drain that steam trap at a lower pressure to grade or to a pump, and then flash off to the lower grade pressure.
Yeah, okay. I mean, there is a few ways we actually do address water hammer. It's not like we always come across ideal scenarios at site, but you could also reach out to us with the specific issue as well, and we'll try to see what we could do to address it. Because again, it becomes, as Jeff was saying, case by case basis. How do you have it set up? What do you have in there? So a little bit of more detailed data might be necessary as well. Okay, let's go on to another one. Flooded heat exchangers, water hammer in flooded heat exchangers. I've seen this happen in flooded heat exchangers if they're not properly designed for the flows. We've actually seen it happen on some of our flooded heat exchanger designs, but we've addressed it by ensuring proper control system in place, which doesn't allow a continuous hammering of steam on the flooded heat exchanger itself. So there is a little bit of design consideration in these. So again, these will, in my opinion, these will need to be looked at as well, because if the design is not right, if you just put a valve on and there's no proper control mechanism on it, you will have water hammer in flooded heat exchangers, which will ruin the heat exchanger itself, and the heat exchanger can cost quite a bit. Jeff, have you seen the flooded heat exchangers issue with water hammer in there?
Most of the time with flooded heat exchangers, we see a lot of flooded heat exchanger out there that are non-repairable. So the issue becomes, again, as I discussed in the process pressure area, a lot of these systems are designed for radiant heating systems, where my process or my radiant heating systems are on variable volume pumps, save energy based on outside air temperature, and when I modulate those pumps down, I lose pressure. I could be operating my flooded systems at a very, very high pressure, and high pressure I mean relatively low pressure, 80 to 100 psi, and we boil the process water or glycol. It's not good.
Yep. Yeah. Okay. There was one question about when Jeff was showing how vacuum or collapsing bubbles will cause water hammer. I mean, it does cause water hammer in steam pipes very often than not, as Jeff was talking about it as well. Because if you have a full, as Jeff was saying, if you have a filled up line with water and suddenly you have pockets of steam which start collapsing, that's what causes water hammer. Vacuum is favorable in heat exchangers, but you have to design for vacuum. If you don't account for vacuum in there, you will have a water hammer issue. If you do account for vacuum in there, you design it so that it's vacuum is, you address the vacuum as well. That helps because steam under vacuum has a lot more or has a little higher latent heat to give away. So that would actually help in there as well. Jeff, when you were talking about it, you were talking about vacuum in piping systems more than a heat exchanger package which was designed for vacuum, right? Or
well, I agree with everything you said. You know, we most heat exchangers, and heat exchanger design course is I can't complete it in another half hour. It's another half-hour presentation in its own on
Agreed.
excess surface area, stall, et cetera. But if we design, and it's pretty simple in my mind, every system out there on a process site is going into stall. So if we assume that, we just need to design for that, and it's going to go into vacuum. So it's very simple. Just design for that, and then you'll never have a water hammer issue in a process heat exchanger.
Yep, agreed. I have another question here about high pressure. A good remedy for high pressure converters that are feeding variable volume perimeter systems. How can you regulate steam to reduce flooding and water hammer? On these, it's, in my opinion, the way to reduce water hammer and flooding is to ensure proper drainage. And what we propose in these cases is either a closed loop system, which will ensure there is no flooding at all, and it reduces water hammer because there's no flooding. And also, in the same note we were just talking about, you could also potentially run that high pressure converter under vacuum inside the heat exchanger. You might be feeding it high pressure, but inside the heat exchanger, especially in a day like today. I'm hoping a day like today is across Canada really warm, and a day like today, your perimeter heating system is not running full out. It's possibly running at not even 10%. So a day like today would be a problematic issue for systems that were not designed for this, and systems that were only designed for the coldest day. They will be water hammer in there and flooding, and that could be reduced by proper gravity drain. Even with gravity drain, there is a risk of water hammer, but you could also reduce it by a proper condensate removal system, making sure that it's the best one. So, Jeff, thoughts?
Yeah, the only issue there, again, it brings up more questions than answers. I need to know if there's a control valve, or can we add a control valve, and the costs involved in that. But yeah, everything can be fixed. It's just a matter of looking at it and trying to determine, what's causing this water hammer. I agreed with what you said.
Yeah. There was a question from Andy about extremely slow, like warming up a steam system extremely slow, 10 to 20 psi, that was offline for a few hours without draining condensate at low points. Find this works for them in the 200 psi system. I have next to no water hammering. Do you advise against, or is it slowly warming up okay to push condensate to our recovery system?
Yeah, the low pressure side is a little bit more difficult, and you can do it. You just if it's for a short term, like I say, it asks a lot of questions. How short? Are my lines completely insulated? The more insulation I have on my condensate return lines and my steam lines, the longer I have to keep that temperature. Sorry. If I go back to if I keep my subcooling to a minimum. So again, insulation is critical in those situations where a maximum insulation will give me a lot more time to maintain those temperatures so that water hammer will not occur. If that still doesn't work, then we have to look at some different solutions on the low pressure side. Draining the signs, automatic drains, steam traps with different orifices so that they work on low pressure or lower pressure, shut off at higher pressures. There's a number of options, but yeah, you have to look at that.
Yeah. So also, Andy, I think it might be the reason it might be working is maybe your back pressure is not. You still have enough pressure on your condensate line to move the condensate, and your back pressure is not as high. But in scenarios where the back pressure is high and the condensate still keeps flooding inside your inside your system during startup, you might get water hammer. And I've actually noticed it even in our lab here. When we start up, we get a little bit of water hammer, and we have to drain out the low points because our back pressure is a little higher than the warm-up pressure, right? So that would need to be as well. Another question: how can we minimize water hammer caused by flashing of high temperature condensate in lower pressure piping, leading to a feed water tank, for example?
Simple. Separate the lines. I know that's easier said than done, but the lines should be separated from design stage. But yeah.
If it is not a lot of high pressure condensate, depending on what you have as well, Mustafa, there might be ways to do this. If you have piping installed already, now the best, as Jeff said, is separate it. I know it might not always be a easy thing to do, but there's ways of doing condensate mixers, which might reduce it a little more as well.
Agreed.
Actually, follow up to the perimeter converter. Most of our perimeter converters were retrofitted with VFD pumps. Yeah, very, very, very often than not, that is the best way to do it. But the design problem, I wouldn't say it's a design problem. It's a design problem on the converters itself, because the converters have to be also in tune with your VFDs, because your steam to hot water converters, if they're blind to your VFD flows, then you will have problems because they don't know what's going on with the VFDs. So because they're designed for a condition which is, as I said, the worst case scenario, full flow. That's the condition they're designed to, but we should, and we do, design them for VFD conditions as well. So we always ask that question: are they on VFDs? Are they at constant flows? And sometimes it doesn't matter. Even if they're on constant flows, in the future, customers want to save energy, they move over to VFDs. We want to make sure that the systems we provide are pretty much self-sufficient without you trying to change these out. So, but do reach out to us, Dawood, on that. Maybe there's a little bit we could do as well. Is there a general rule I should follow between choosing a vacuum breaker at each steam radiator versus a vacuum pump? So a vacuum, so Abhishek, the vacuum breaker will address breaking the vacuum, but all that does is make the system of your radiator to 0 psi, right? Because it basically makes it to atmospheric pressure. That doesn't essentially mean it will still flow. There might still be a little backup on it as well, backup of condensate. So the vacuum pump, instead, what it does is it keeps the, and the vacuum breaker also introduces air into a radiator. So when you put a vacuum breaker in, you need to ensure that this air also leaves the radiator, because air becomes a really good insulator. And especially on a radiator where you're trying to get heat out of it, filling it with air will not do any good. And air might also, depending on the type of the radiator, it might also start eroding the radiator, and you get those sort of corrosion issues at that point too. Which is why the vacuum pump is a better solution, because then the system's closed, you don't get external air coming into it, and you don't get water hammer as much. So the vacuum pump is typically connected on these radiators at the end. So all of these condensate from the radiators go into one vacuum pump, which is basically pulling condensate from the system, especially in these ones where the steam pressure is like 5 psi or less sometimes. So hopefully that helps. Any other questions? Can you use a spring check valve in a steam system? I'm not sure. You can, when you say spring check valve, I'm trying to think.
Yeah, no, I can answer this.
Yeah.
Yes, if you're gonna use a spring check valve, again, a lot of questions need to be asked. How big is the condensate line? How big is the check valve? Those type of questions. But yeah, as long as you're using all stainless steel components so they don't rust together over the summer, you should be okay. If not, you might have, if you use steel components, you might have to go around and tap them with a hammer to get them broken free for the winter. But yeah, you can use a spring check valve as long as it has a very, very low cracking pressure.
Yeah, actually, I was just gonna say, Jeff, because we've had this issue where we've used, or customers have used spring check valves, and they had a really high cracking pressure. Some of them as high as like 10 to 12 psi G. So, and they were using it on low pressure systems, which meant the condensate just backed up. So we use spring-loaded piston check valves most of the time on these, and we use our most recommended one are disc check valves because they have very, very minimal cracking pressure itself. On steam and condensate side, we use what we call disc check valves, and quite a few of them are all stainless steel as well. I mean, they're obviously slightly more expensive than the piston check valves, which are not stainless steel. But the piston check valves, we don't put the springs in, and it brings down the cracking pressure to a little more bearable in the system. But please ensure the cracking pressure is also right in the check valves as well. So, trying to see, Jeff, in your earlier comment, are you suggesting to insulate the condensate line?
Absolutely.
Yep. Yeah, I agree with Jeff.
Yeah, absolutely. The hot condensate line, because if we look at it from an energy perspective alone, not a water hammer issue, if we look at our hot condensate lines, they're really, you know, I use the term 0 psi steam lines, but they could be up to 10 psi steam lines, and very little water volumetrically. So they're basically the same as steam lines. Now, pump condensate lines, no. Should you insulate them? Yes. What's the radiant temperature off them? Very low. But yeah, hot condensate lines, yes, definitely need to be insulated.
Awesome. We had a few other ones like transient study request. We had some on more elimination. I hope we covered some of these already. But if you feel like there's any other questions, please reach out to us, reach out to Jeff, reach out to your local sales rep, or reach out to even our common customer service line, and they will pass you on to us. Please feel free, and thank you for your time as well. Jeff, I'll leave it to you for closing.
Yeah, no, thanks guys. Thanks for everyone. Hopefully we answered most of your questions. If not, we're a Zoom call away. You have my email, you can reach out to me, and we'll do our best to solve your problems for sure. Thank you very much.